As we have seen, we had been working on linear regression, which is a simple linear regression. We went to multiple and polynomial regressions, but still there are challenges. What are the challenges? Last time, whenever we were working on the models, they were underfit, right? Sometimes there could be overfitting. Overfitting happens generally with not with regression, but with decision tree kind of models. When I come to decision tree or random forest or extreme gradient boosting, that is XGBoost, I'll discuss those challenges. Most of the models which we deal with majorly are having the underfitting issues. Can somebody let me know? Sometime back I discussed underfitting, overfitting. Can somebody correlate or discuss does when does a model is underfitting, when a model is overfitting? How do we correct that? The basics.
Overfitting when the higher values are like way too much. And I think we have to do that downsampling for that.
Okay. So let me disable this floating meeting control. Now let's understand what is a model fitness, right? When it is a overfit, when it is a underfit, when it is something known as a good fit. Okay. Screen number one or the chart number one says that the model is underfit. All right. Visually, what you see, why you see it's underfit? Underfit means what, you know? Very simple. Model is having poor accuracies. Overfit means model is having 100%, 98% kind of accuracies. There is no criterion to mark underfit, overfit, right? Sometimes if the model is generating 89%, it is underfit as compared to 95% accuracy. Correct? So we don't know when it is underfit, when it is overfit. There is no standard. But let me give you a certain threshold. So any model which is having poor accuracy, it's a underfit. When any model is having maximum possible over, let's say accuracy, it's a overfit. Maximum possible is like close to 100, more than 95 something. Underfit is something which is less than 60%, just as a threshold. So what is the why exactly we call the first chart visually as underfit? I'll come to the logic next, but from the chart, why it is underfit? There is a standard red line and there is the actual data points. This red line is nothing else but our actual data points, which are plotted for every observation using the equation y is equals to a plus b of x. So if I implement on my data in my model this equation, so that would be having two parts. Number one, if you can see this red line, which is my y is equals to a plus b of x, using the formula model, I can create that. And this observation x, 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 whatever you see, it is basically the actual values of the data. Why it is underfit visually? Anybody? How do we say that it's underfit?
It's not able to capture all the points.
You can calculate RMSE error.
Yeah. So first, I'll not be discussing statistical, right? What I'm discussing is visual.
The data points are far away from the line, whatever it is, the model predicted line. All the data points are not like the error is moved. Maybe.
So this is correct.
I think on the fit line, number of points are lower.
Yeah, this is correct. This is close.
The thick points are not closer to the thick line.
Exactly. So rest of this are like the outliers kind of things, like not at all in a range to predict it, right? On downside also, you'll see that these kind of observations are very, very high errors. These are closer to the line, right? So we are very close near the prediction, right? I'll teach you something in the next session, probability and distribution. Ideally, what do we do is, we try to create a normal distribution again on this. Let me show you here. So let's say if I create a normal distribution. Okay. Now what is the case? Let's say there's a lower control limit. There's upper control limit. I said that -3 standard deviations to +3 standard deviation is the range, and maximum observations are lying around the average, right? In this case, few observations would be extremely higher or lower. So from the probability part, I can devise a model which can at least give me a acceptance and rejection region. So therefore, most of the times we call it Bayesian. Okay, or probabilistic models actually give a better understanding. So when we say if I want to predict sales, tell me which is better. I say that okay, I'll be having 1500 units of sales versus I say that let's say with respect to with a RMSE of around 5 units, or if I say let's say there would be 1200 units of sales and the lower control limit is going to be around 2 units and upper control limit is going to be around 2 units, right? You'll find that here we are using RMSE. Here the units are actually calculated on the basis of probability. So instead of unit wise, you will come to know the lower control limit is basically nothing else here, but it's a kind of a percentage probability. So let's say I have 98% confidence that 1200 units of sales would be there. Okay, like that. So that confidence interval will be worked out. But let's not get into that detail right now. What I am saying is that when I will be showing you the plots, I'll go to the next level in terms of Bayesian side of operations. Right now, you just have 3 visuals in front of you. What are those visuals? These are the basic visuals, which says that I have one particular chart which has observation far away from this line and certain observations below this line. Underfitting, if you understand, is happening when you have, let's say, divided data into training and testing, right? We already say that we have training data, we have testing data. Most oftenly, underfitting happens when your training accuracies are, let's say, accuracy of training data is low and accuracy of your testing data is, let's say, high. In overfitting, what happens is my training data accuracy, when I'm testing my model on training data, the accuracy is high. And when I'm training my model or predicting the values for my testing data, the accuracies are less. So one is visual representation of understanding underfitting and overfitting. One is understanding from the training versus testing kind of difference. And third way to identify overfitting, underfitting is with respect to bias and variance trade-off, which I discussed a long time back, if you can remember. Okay, guys. There are 3 ways by which we can identify overfitting and underfitting issues. One is visual mapping, or let's say with error scores. So we can visually see that the straight line is going there. There are less number of observations on this line, which means that actual predictions are much lower. In this case, this model is trying to cover almost all the observations, which rarely happens actually. So it is good for a training data, but for testing data, when we go live with this application, it may fail because sample is very large. So now I'm going to third part, bias and variance trade-off. Whenever your overfitting case is there, you please consider that in this case, the data, training data is very large or huge. What happens is when training data is huge, we are actually almost closer to 100% in predictions. But what happens is if there is a drift in the data in real time scenarios, this model will not work because when it comes to testing data, the accuracy are bit lower. The reason is testing data sample could be low, which leads to another level of overfitting, underfitting issues, right? Why underfitting is there? Because testing data is more and training data is less. So for testing it works, but in training data we don't have accurate and let's say large number of observations, and therefore model is failed here. Ideally, we don't require either underfitting model or an overfitting model. So we need a good fit model. To understand good fit, you need to understand this matrix which I'm creating. Okay. So this matrix basically is nothing else but a bias variance trade-off. What is bias? Bias is nothing else but, I understand right now, it's y predicted value minus y actual. This difference, if it is more, you say bias is more. What is variance? Variance is equals to y actual minus y average. If this difference is more, variance is more. What is variance? It's y actual minus y average to the power of 2, right? Summation of this. You remember that? And divided by total number of observations, which means variance. And under root of it is standard deviation. Is everybody clear on difference between the formula of bias and variance? Please confirm. This is a predicted value, which is nothing else but its outcome of a plus b of x kind of equation. This is your actual data. If this difference is more, bias is more. If your y actual, this is the real data which you have versus the average of your actual data. If this difference is more, variance is more.
One
And-
doubt, Dr. Ravi. So
Yeah.
if the variance of data is very high, can we assume that the model fitting will be difficult?
It will be overfit always. And why variance is high? Because data samples are very large. The observations are having huge gaps. One lowest data is starting with 2 units, and let's say the last observation is something 100,000. So you'll see that variance would be definitely higher. We have a lot many observations. Like it happens if you start calculating or if you work on regression model on stock prices. If you start today prediction, if you take more data, like let's say span of year 2000 to 2025, you will see that the stocks would be trading at around $10 in around 2000. Right now it may be 750. So the gap is more. The observation point is more. The window is more, right? Event window is more. I mean, it's very wide. So therefore, this part would be wide. But whenever this part is wide, you'll find that accuracies are going to be improved for training data. Okay, that's why if you take large period of observations, prediction for the next day would be very correct. But when it comes to prediction of after 5 days, there would be distortions because the variance part was very high. It's all interconnected. To keep it simple, let me come to my whiteboard, right? I think that would be easier for you. I couldn't understand yes or no, so audience, please let me know that.
It is clear.
Are you following me?
On bias, I have a question. So if generally I've heard people saying that if the model is predicting it's memorized, then it is the bias is very high or the model is biased, right? In that case, shouldn't y predict minus y actual should be very less for the model to be biased?
Not actually, because reason being is that bias is still there. I mean, we can't say even bias a bias. unless this gap is there. You getting it?
Okay.
What is bias? The model is not predicting well. It is under fitting kind of a issue.
Okay. Okay.
And when underfitting happens, accuracy is poor. And when accuracy would be poor, when this gap is more,
Okay. Okay. Got it. Okay.
right? So please understand, it's all like interconnected, and that's why to clear it, I need to take my whiteboard actually. Otherwise it would be. Okay, sorry. Let me before that remove this. Let's avoid annotation. Come back to the. So it'll take another couple of minutes, 15-20 minutes. After that, you'll understand regularization also. Okay. Come up. Okay. And how do we relate with what is that? Underfitting and overfitting? We are discussing that aspect. As I mentioned, if you have more complexity, okay, or in data or model, okay, how data is complex, large number of observations of training or testing data, and model is maybe you're working with high dimensional models like neural networks, like decision trees, like random forests, like XGBoost. There are certain categories of model which are working on high dimensions with n-dimensional arrays, right? Neurons and all. So these kind of models also have model complexity, or we have a data complexity. So wherever model complexity, data complexity is high, actually the y predict minus, sorry, y actual minus y average, this particular deviation would be very high. That's what is known as variance. Reason is we have a very high set of dimensions of data or model. And in that case, whenever you are working, the training accuracies will be very high and testing accuracies will be less. That's what is termed as overfitting. Is overfitting clear to everybody? Why it is happening? What are the aftermath and the reasons behind that? Whenever the data is, or a model is having large set of complexities, the y actual and y average part would be high, and in that case this particular training accuracy would be high. Testing accuracies could be low because we don't have that much of records or dimensions in the testing data, and therefore this leads to overfitting. And in overfitting you see that you have the line which is trying to cover up almost all the observations. Model accuracies in this case we are finding is 98 to 100%. In one of my client, when I was working, we are getting 100% accuracies with a university setup when we are predicting the churn rates. We tried everything. Okay, I'll show you what we try in that case. We tried everything, but today also in the development aspect, which is now a production stage environment, also we have created. There also we are having high accuracies. So which means that we have understood the scenario very well. But in a long run, the chief executive officers are not going to believe that. Reason being, they say that how can you identify the drifts which are going to happen in future today, and this is that how we can get the future 100% accuracies. So that is another thing. I'll come to that discussion at a later stage when I discuss hyperparameter tuning. But right now, to digest, we have variance which is high. Okay, very quickly, when variance is high, anybody? And what is variance?
Data or model complexity is high.
Yeah, so when data and model complexities are high. And what is variance?
Y actual minus Y average.
Right. That deviation would be higher. And what will be the outcome?
Closer to the 100%, which is not
Right. Like
acceptable.
for what? That is more for training data, right? Yeah.
High training data and less testing data.
Correct. Now
Larger.
let's talk about bias. The brother bias, if we talk about, it's basically nothing else
Yeah,
but
predicted values and actual values when just by difference.
yeah. In simple words, it's like y predict minus y actual. This deviation is going to be very high. Ideally, what we do is we will take root mean squared error. So summation of this and the deviation divided by total number of observations. That's how we calculate it. But the bias part is, as you see, the major foundation is difference between y predict values and y average values. And now if you see the formula of root mean squared, sorry, r square, I said that it is 1 minus summation of y predict minus y actual divided by summation of y actual minus y average, the whole square. So in short, r square is nothing else. It's 1 minus error. And what is that error? 1 minus bias divided by variance error. Isn't it? So this is what r square we studied last time. Okay. So this portion is bias. This portion is variance. So if you see variance is high, okay, let's say variance is high, what will happen, guys? Let's say bias is low. So this portion will be high or low. If variance is high, this item would be high or low?
Low.
Low, right? So let's say, assume that this low is 20%, okay, 0.2, which means that now you can see accuracy is high, right? 1 minus error is what? Accuracy. So accuracy is how much? 80%, correct? So it is proved that whenever variance is high, this numerator divided by denominator, this portion is going to be low. Because this is low, accuracies would be higher because this R square is what? 1 minus error, which in turn is like one your accuracy only. Though we don't call it accuracy, we say that it is model's explanation power. Okay, the right jargon is it's explainability of a model. Okay, the percentage of variance explanation, that is the right thing. But don't get into that R square right now. I just shown you that how it is related with R square. Okay, so let's find the verdict. So whenever your model is there, any model which you built up, right? And the thing is that when you talk about bias part, if the model complexity or data complexity, you know, is low, what is model complexity? The XGBoost to neural networks kind of, structures. Or data means, yeah, or data, which means that when I'm dealing with low dimension data, or let's say less number of records. Let's say I have only three variables to study or to predict whether India will win the match or not. It depends on, let's say, weather. It depends on wind, and it depends on, let's say, any other aspect like whether I say it's like cloud or sunny or something or rainy, and let's say the last part could be humidity. On these basis, if I say India will win a match or not, it is very risky, right? So these are like, you know that there are not much explanations. Why happened? Because data is low, right? Less number of records or variables. So it could be records which are less, or it could be number of variables also which is less, which is dimension. So therefore, this complexity is low. When complexity is low, errors would be there, isn't it? So you don't predict well, and the training accuracy would be low. But when you actually go for a testing, it can be high. So reverse. So in short, are we clear? Please confirm any doubt till here. Very quick.
How is testing accuracy
Why?
high? Yes.
Mhm.
Because when we trained, the accuracy was low, right?
See, this is not proven thing. This is just hypothetically you have to adjust and you have to prove that. What is understanding is, in short, your training accuracy is low. Sometimes what happens is when you're testing it, let's say you are working on a 3 days record, but you when you create divide data into two parts, by default what you did, you created a huge data which is testing data. So you did opposite, right? 20% training data, 80% testing data, right? In that case, it could be that the testing accuracy would be higher and training accuracy by default would be low. So that's why most of the times what do we do is we try to keep it 70-30 sort of, right? Overfitting is good because that gives us confidence that, okay, my model accuracy is more than 90%. So these are all hacks used by statisticians to impress their boss. Nothing more than that. So I can manipulate my model. I can manipulate my predictions. And that's deadly game.
So Ravi, this 70% will be the testing data or it will be the training?
Oh, training it.
Training.
So always training come first and followed by testing. Yeah. This I'm seeing on train test split method, right? Test size is 30 or 20, which we keep. That is why that is kept. Now you got a logic, right? Why we keep less data on testing part. So you won't see that, people are training like 50-50, right? Sometimes you might be thinking of that scenario. Why don't people take, 50-50? Because people deliberately are biased. They say that, okay, I want to have some more accuracies, right? And when it happens, when training data is large. So this is a statistical biasness manipulated in the best possible way without making a particular person who is non-technical understand why these accuracies are higher. It's all mathematical game, right? I can get any particular model highest accuracies, but that should not be the case, right? This is right. We are playing with people, money, and all. So I'll not discuss those tricks. Now let me summarize in a easy way, so you can remember it for lifetime. Okay, so let's understand bias, variance. Let's say low and high, low and high. Tell me what will happen next. So when bias is high, and let's say variance is also high, or let me come up with one more scenario. When bias is low and variance is high, what is that scenario? When bias is actually low and
Overfit.
variance is going to be high.
Overfit.
Overfit.
That is overfitting, right? So overfitting is what?
Bias is
low.
low and
Low bias, high
bias
bias.
Right? So ideally, I have to design like that. I think like this, right? High and low, isn't it? So let's see, bias is low, variance is also low. It is also not a good fit. Underfitting is what? When bias is
high. Variance is low.
and variance is low. So bias is high, variance is low is this case, right? This is my variance part, right? Which is low. This is my bias part, let's say, which is high. So these cases are uh, underfitting. When my variance is very high and bias is low, this is what is overfitting. When bias and variance both are low, okay,
Not a good.
A good fit, right?
this is the, yeah, you can say a good fit or optimally fit, right? This is something weird. Bias high and variance high. So it's beyond overfitting, beyond underfitting. You don't know like what is the scenario. It's like completely outliers, right? Here you'll be seeing those things. Very risky scenario. This we don't want to even think of. Bias is also high, variance is also high. It's very rare situation, and this is questionable. It may be because of outliers. So this case is invalid. Bias is low and variance is high. This is overfitting. This is good to impress, but bad actually for customer. Underfitting is what? When bias is very high and variance part is low. This also nobody wants. We need bias and variance to be lower. Now graphically, how you understand that? Last thing, okay? Then I'll help you to how to cover up this. So let's say this is model complexity or data complexity. And this is your error. So when complexity is less, what part is high? Bias is high, right? The error is high because of bias. The error is high when complexity increases. This is because of variance. So by for sure, very rare situation would be that variance is also high and bias also high because there is a huge gap. And what is most probable thing that complexity, if it is increasing, its variance is increasing. When it is decreasing, its bias is increasing. So error is actually something which is bias plus variance. Sometimes we also expect errors, right? 2% error would be there. So it is expected also. So this is your total error. So total error is what? A bias part plus variance part plus expected part. I'm discussing everything from Andrew Ng's very nice explanations. If you have listened to sessions of 2012 something, there he has made very clear the total error calculation is based on bias plus variance plus expected errors. Now see what is the trade-off and where do we need to see this. This is where you can see is the optimal thing, right? Before this bias increases, after that variance increases. So we need that intersection point where error is the manageable thing. Here, see the error is going to be the least, but in that case, what you see is there is like these situations are very much idealistic. Okay, model complexity is very less, so bias won't be there. I mean, the variances part is less obviously, but bias would be very high. So this is also less observable. What is observable is this part which we should see. This is the total error. Then how do we do that? Let's see. There is a concept of regularization. I'll come to the hands-on just after that. So there is a concept of regularization. What I mentioned is, if you draw an equation or a graph between x and y, the straight line which goes like this, which is y is equals to a plus b of x, is a straight line, predicted line you can say, y predicted. Above that there are observations and below that there are observations. To cover up this observation under this, the line has to slightly go up, isn't it? But at the same time, line has to go down also in this case for two separate observations, which is very much difficult to handle. For sure, this is not right optimization. The data, the model will either go high or low. But for this, it is doable. Where the relationships are not straight, they are curvilinear. Like for example, again I have this one observation here, one observation here. For meeting this two, line should go up one time, should come down one time. Okay, what is this line? Y predict, which is a plus b of x. What is a? This is y average minus bx average. What is b? It is summation of your let's say x bar minus x minus x minus x bar into y minus y bar divided by x minus x bar, the whole square, and summation of that. This I will discuss, right? The mathematical equations. So y is equals to a plus b of x. To make this line shift up, there are two ways. Either you shift a, the constant is what? This is your part a. So either you shift this constant a from here to there. Okay, manually. We call it iteration, right? So iterations could be there by model automatically. So a is also shifted. At the same time, this b also can be shifted slightly upside. So when a is shifted, this part is shifted. When b is shifted, this line is shifted. So this line comes from here to there. How come? What shall I do, guys, in this equation? Please tell me. To shift this line up from here to there, in this equation, what shall I do? Shall I multiply this b, which is already a weight, with another weight, which is in multiples of 1, 2, 3, or decimals like that? Will it shift up?
Yeah, I think so. Because you are
Yeah.
increasing the x.
So here we are attaching a penalty. Okay. Let's say penalty number 1 multiplied with bx in such a way that this penalty is positive integers, right? How to bring this slope down? This is a slope, right, which is b. So how to bring this slope down? Again, there are two ways. Like constant a also will be down, right? Like that also you can draw. So there are two possibilities: optimizing a and b, right? So the next equation is y1 and y2 is that I can implement penalty 2 with respect to b, which is multiplied with x, but this time penalty 2 is in decimals: 0.2, 0.3, 0.001, like that. So what happens is this particular b portion is decreasing. Am I clear? Please confirm this. There are only these possibilities.
Not clear, doctor. You are going to cover both the points, or
Both the points. Actually, when you see the gradient descent, which I discussed last time, A is also tuned and B is also tuned, which we don't see because model is running behind the scenes. When I'm saying model is running, it means all iterations are happening, right? There are thousands of iterations which will be tuning this value, that value. So you can't even imagine, right?
But
What we are doing is the target is see how the model is written. Minimize y predict minus y actual from the with respect to the equation y is equals to a plus b of x. So there is a minimization function which we create. So how to create that? N number of calculations should be done where a plus b of x, when you work out this y predict minus the y actual, if you do, that is almost zero.
Doctor, one question. Whatever the
Yeah.
model finally we are targeting to get, it will be a linear model or non-linear model in this explanation.
Any case, be it linear, non-linear, whatever, the prediction equation is changing, right, as per that. So polynomial regression has its own equation. So you can see that the coefficient will be b only, right? It will be nothing else, or it would be b square. The weight will be attached to b and a both. So ideally, if you see now, there are two equations, or let's say two possibilities. Okay. Number one, equation one, let's say weight 1 or attached with a plus weight 2 attached with b multiplied with x. This w1 and w2 actually are to be tuned. In y1, I am saying that increase the particular slope or the constant. In second kind of iterations, weight 1, let's say weight 1 dash multiplied with a, weight 2 dash multiplied with bx. Slope should come down. So in that case, multiply with decimal values. This W2, right, kind of weights should be in decimals. And this should be in what? Positive integers. This
But
will,
last
yeah.
Sorry for interrupting. Last week when we did linear regression, right, you were kind of printing the coefficient, right? There was only one coefficient, which means that was only one weight, right? So how can you fit both the points if there is only one weight? In this case, you have W1, W2, and again for Y2, you have a different weight, right?
See. This is not our manual operation. This is all done by model, which is highly powerful compute engine. Just understand. So what I am just asking my equation is to minimize y predict minus y actual, whereas a plus b of x minus y actually, if you do, should be closer to 0. You getting it? It's a automated command which I give. And what happens? This is iteration number 1. This could be iteration number 2. This could be iteration number 1000. I don't know. So it's all in the hands of my model, which stops only when this part is going to be lesser than 0.
Okay, understood. Okay.
These are all iterations. I'm not saying this too, but there could be thousands. In neural network, it could be hundreds of millions of iterations, which can be possible. But it will take time. The more iterations you do, it will take hours and days, right? That's it. So tell you one more last thing on this. What is a gradient descent? Gradient descent is nothing else but a 3D modeling in such a way that this is your error part, this is your constant part, this is your weight one, the B part, slope part. So we try to get, okay, multiple observations like that. The best observation is that where the error is the least, and I identify this should be the A and this should be the B value over there, okay, where error is the least. That's my objective. How come it happens? So you write the equation there. What is that equation? You see the change in, let's say, weight, or let's say new weight. In every iteration, there would be a new weight, which is identified with respect to old weight, okay, minus, let's say, rate of change of your y predict with respect to the rate of change of your item x, or let's say y actual with respect to rate of change of x. So don't get into that right now. I'll come back slowly in every aspect. But is this clear that these are the quick hacks? Two sorts of things can happen. One particular thing is, this is known as regularization. What is regularization? To make model good fit. If it is overfit, bring it down, bring the variance down and make it good fit. How come variances can be down? Anybody? If data is overfit, how variance can be lowered? Or accuracies should be lower? Because ultimately overfitting is what? Accuracy is high. Please tell me. We assign penalties. So in the equation, y is equals to a plus b of x. When I say I'm multiplying this b with additional weight, which is in decimals, don't you think so? This particular coefficient's value would be a bit less. And ultimately what would happen is, when I'm comparing with respect to this y actual, this y predicted values could be slightly higher or lower, whatever, right? So we're actually making changes in the equations in such a way that the weights can be manipulated. So we assign penalties. These penalties are attached in two ways, L1 L2. L1 penalty is basically known as one method of regularization where we are attaching the weights, and the squared one is what? It's known as ridge regression. This is lasso regression. Okay, there are two types of regression models or penalty models. One is lasso, one is ridge. And this lasso and ridge I have discussed with you. Let's come to the formula of lasso and ridge. And then you tell me which is lasso, which is ridge kind of equation. Remember, guys, what I'm doing is trying to regularize my model. Regularization is what? Bringing the model from overfit or underfit to good fit. When overfit is there, bring variance down or attach more penalties. So, or let's say noise in the data. So you get less errors. Sorry, you get more errors. But when underfitting is there, you increase the model complexity or the variance. So you get better accuracies. So increase more data points, increase more dimensions, bring more new variables. This will improve your underfitting issues. But when you are getting overfitting, try to lower the number of observations, try to lower the number of dimensions, try to add noise to the data. This noise is nothing else but again the penalties. Okay. Now let's see lasso and ridge regressions, kind of equations. And I'm sure you'll be able to get that. The only difference is that in both of this is that in lasso, one more thing I'll discuss. In lasso, when I'm writing the equation, you'll find that when I'm dealing with lasso, you will see something that I'm taking, let's say, when I'm talking about, the equation y is equals to a plus b of x. So I'll be attaching the lasso penalty as a plus, let's say, penalty 1 into b of x. But when I go for a ridge, you'll see that I'm attaching more penalties. So it will be p2 square into b of x. Are you getting it? So when overfitting is there, you can use this model because this will be a very rigorous penalty on your weights, which is coefficients. And when you're applying this, this is lightweight penalties. Like you can bring down the accuracies to, you're adjusting the accuracies, but with less penalties. You're attaching more penalties when your model is highly overfit. So let's see these equations. Then you will tell by default that which is ridge, which is lasso. So I'm going back to new page, ridge and lasso equations. Hey guys, what is this? What happened or what? Just give me a second. I think it got some issues. Maybe, okay. I'm sorry. Because of annotation, it is not working. Sorry. So let's restudy this, right? What it says is, I am randomly coming to this. Understanding bias and variance. To comprehend overfitting and underfitting, we divide with bias and variance. Bias represents model's error when dealing with training data, while variance signifies the error when handling the testing data. Underfitting is what? It occurs when model's accuracy on training data is a bit less, leading to poor performance on testing data, right? So,
Mention that
ridge
both
and
are
lasso.
below. Dr. Ravi, if you go top, okay, it is mentioned both will below bias and variance.
Sorry.
No, it was mentioned that both will be lower in the comment there.
This says both is lower, but standard is that when the training is bit higher and testing is lower. It depends on the author, but ideally scenario is that. Just give me 1 second. Huh? Sorry for the intervention. So that's why I scold that. Don't get into that. I think there is a gap. You just focus on Ridge and Lasso for this article. So when I said Ridge and Lasso, guys, what basically they are known as? I said Lasso is what L1, and Ridge is what L2. The name suggests that whenever R is there, square has a R. I mean, how I remembered it, because R and squared item there is R is common, right? So Ridge is a squared one, and therefore L2 is basically kind of a square for me. So I always remember like that. I don't know. You can remember it by default, but it was always confusing. So I said that okay, L1 and L2 are nothing else, but the first is always lasso, and second is one is always a ridge. That way also you can understand. So how the high variance, low bias, and all these things can be tweaked is basically that's why ridge and lasso kind of regularization techniques have come up. And what is this regularization? Ridge regression, as I mentioned, it has a kind of a squared approach, right? Right. What they are doing is they are attaching a weight and taking the square here, on the B part. Like it is attaching more penalties, kind of. So the penalty is there, and in some cases, you even square up the penalties also. If the data is, or let's say accuracies are really very, very high, in that case, what you can do is you can further increase. It's all in your hands, right? Nobody is going to control you in that case. It's up to you how you come up with the equation. So the idea is that I'm having the cost function or the error, which is not either underfit or the overfit. This lambda is nothing else but P, you can say. And what is this, guys? This is like y predict, right? Minus y actual and the square. So this is the error part. In the error, I am attaching additional penalties. Please see to it. What they're doing is, let's say this is my error part, right? Plus, I am attaching penalties. So what it will do? It will increase the error or decrease the error?
Increase the error.
Increase the error.
Right? It will increase the error. And when I increase the error, when my objective is what? I was having something overfitting, means high accuracies, like 100%. So I try to ingest this model, regularization techniques, to deal with overfitting issues. So regularization basically comes with what? They come with the approach of bringing overfitting to underfitting. How you do that? You attach the penalty to the error already, which is there. So where we do that? We do that change with respect to the slope, the b, right? So either you can have lambda square multiplied with b and also take the b square, or you take lambda into b square, but take the items as a square. Okay, that will be one approach. See the difference with lasso L1. What is the difference? Let me clear this and annotate. This is error part same, right? Plus this error equation y predict minus y actual the whole square. That's it. Error, root mean square error, you can say. So in the error, I am attaching the penalty lambda again, but with not squared values of b. No, That was what? Ridge. Ridge is squared. L1 is nothing else, normal. So L1 comes with absolute value of slope. What is absolute value? Slope could be minus also or plus also. So if it is minus, let's bring that to plus, absolute value. So there is no square. So this is lasso. So it depends in what case you have to go for a squared approach, in what case you have to go for normal approach. Generally, what happens is when my B1, B2, B3, okay, let's say there are multiple regressions, so multiple slopes are there. So B1, let's say, is 8, one single unit. B2 I'm getting is 12. B3 is 1000. Just assuming. So this is not properly scaled, right? 8, 12,000. In that case, you can go for a squared approach, right? Try to get into the squared approach because that will normalize your coefficients B1, B2, B3. So that's how exactly you can manage. If you don't want to get into that deep understanding, simply what you do is attach some penalties to the error already. How can you do that? When you are building an equation y is equals to a plus b of x, in that case, change the value of your a with respect to lambda 1, attach this penalty to a, lambda 2, attach this penalty to b. If you are not taking any squared value, this is going to be lasso. If you take a ridge, it's going to be lambda 1a plus, no need to get the square here. That also you can try if you get something critical. Otherwise, you can take the squared values. Here, the absolute value is taken. Here, the squared values should be taken. That's the only case. And this is how exactly you bring down overfitting issues. And in reverse case, in underfitting, what you try to do is increase data, features. Features means number of columns or dimensions, or take some model like neural networks. You will by default get model complexity higher. But to bring down accuracy, we need to attach penalties to bring down that error. Increase that error. That's how bridge lasso comes to play. This is known as regularization. Okay. So let me know you all good guys. Please confirm. Now let me come back to the presentation so that you can go through that very quickly, and let's do that exercise so that we can get that. So this is to be closed. Uh-oh. This is to be closed. This to be closed. This to be closed. This to be closed. Let me come back. And I think we have weak foot in, isn't it? So weak foot in is dealing with regularization. I think this data set in code, I have to come back. Maybe you are listening for the first time, so you may have to go further again with the session, but try to see the conceptual flow, like how exactly you have taken up what decisions. So let me revise that. Linear regression has basis of predictive models. Multiple regression works with several input variables. Polynomial regressions actually is a nonlinear trend-based workaround. So attaching the penalties to them would be next level game. Balancing generalization overfitting issue is the major challenge. Underfitting can be improvised with respect to adding more data points. Overfitting, for that we need to do a regularization. So this is what underfit to overfit, good fit we see. Next level things are there. Let me avoid this floating control. So the problem is complex model picks up noise. Coefficients grow too large, poor at handling new data. Regularization motivation is what? Bring down the accuracies, right? So problem is what? When the models are complex, the noise is, I mean, the variance is more. I mean, they should not put that noise word. This is variance part. Okay. So variance is more because when I say noise, it means actually adding more penalties. So slight confusion could be there. So model picks up more variance. Coefficients are very large because features are large. It's poor at handling new data set because training accuracy is good, but new data set testing accuracy. This is what is proving my previous thing also. So training accuracies are good, high, but testing the accuracies are less because it is poor at handling new data sets. Solution is what? Add penalties to the error. Loss function is known as error only. What is error? Y predict minus y actual the whole square divided by summation of it and divided by total number of observations. And under root of that, root mean squared error is the loss function. So what do we do? Keep coefficients small. Small, how we can keep small? Multiply with some penalties, which are in decimals. Encourage simpler models. What are benefits? Improved generalization, less overfitting, more reliable predictions. Accuracies are less now. That is also achieved. Then, so as I mentioned, what you can remember ridges, R is coming in a square. So that is L2, which is a square. So sum of a square of weights is taken. Okay. So it is shrinking all the coefficients. It bring down all the coefficients. Use case that when all the feature matter to you, like every variable is to be taken up. So in that case, you can apply weights. Lasso means absolute weights. Instead of taking B1 square, you can take absolute value of B1. Okay. So there are techniques known as elastic net where you can include both. You can actually fine tune the model with keep some penalty on L1 and keep some penalty on L2. Same you can do with what neural networks also. So in neural network, I'll again come back with elastic net kind of frameworks. Let's say how do we implement regularization in regression? So let's have the census record the data from Boston housing. Same data like we used last time. But slightly this is now median house price than house price. So we have more features there actually because overfitting used to be done. Let's see, high accuracy should be there. And we are predicting the Boston housing prices, okay, as per the US census records. The variables are CRIM, that is per capita crime rate by a town. ZN is nothing else, not zinc, but it's zoned for large lots, residential land zoned for large lots. Indus is nothing else but industrial aspect. Chas is basically nothing else but Charles River dummy variable. If river is nearby, not nearby. What is the impact on pricing? If nitric oxides are released, what is the residential aspect? Because that will be underpopulated. In that case, prices would be lower. Age, distance from employment centers, index of accessibility to radial highways, full value property tax rate. All these things are important for predicting house price of a given region. Not house price, median value of house price. What is median value? It is n by 2, total number of observations divided by 2. So for all the houses, the house price are taken divided by 2, and then they have calculated that median value of your house prices. Actually, this data is in $10,000 kind of units. So this is the data set which I'll be showing you very quickly. We'll be importing the basic libraries. Anything new?
This the data whatever you gave or the previous slide is basically it's for the US part of it, right? India may be different.
Obviously,
It doesn't work.
in geographical boundaries, actually things work. When you actually are deciding on any country, one more factor is associated the risk of that country because not every country is that safe, right? Depends on scenarios, political, geopolitical issues and all, war issues and all. So risk is also very important. So that is sovereign risk, country risk. So in country risk modeling, we see even country rating also, the financial stability of the country, right? economic stability of the country, political stability of the country. That all decides the prices, not only the house price, but the stock markets and all the things.
Yep. Yep.
So this is just only sample data set, right? That's why I mean it's for US house price we are predicting it. Okay, tell me any new library you're finding or any new function we are finding. If yes, what is that?
Ridge and lasso.
Ridge and lasso, right? Ridge is L2, lasso is L1. In ridge, what is the equation? With the error, what do? We attach penalties in what form?
Squared form.
Squared form. So L1 plus, sorry, error plus lambda, you can have lambda square or you can also have the B square. And in lasso, absolute value of B is taken. Else other things are like almost same. So we have the house price data where we make changes. I'll come to that. This is predicting the prices with more of the features. Apply polynomial regression also because data is somewhat assumed to be non-linear. So this is X and this is Y. Take all the columns, drop house price, that is your independent variable. Take only the target variable, that is house price, that's your target variable, that is Y. Next step, please. What do we do after that?
Train and test data.
Train.
So split, right? I mean, the ideal word is train test split. So we create a train test split for X and Y. Test size is 20, means training size is 80%. After that, this is the equations you need to work out. Where ridge and lasso is placed, that is important. Polynomial degree is taken as 2, so it's an all squared kind of a model. Model is what? We are taking a make pipeline function from scikit-learn. Polynomial features are taken up. Degree is polynomial degree, which is 2. Ridge is set as 0. So they have ridge is basically 0. That means what? You are almost having no regularization. What it will do if ridge is set to 0? So let's say B square, that basically aspect, if you see the penalty which is attached will actually will do what? Who can tell? What will happen in this case?
It will do overfitting.
It will still be forfeiting. Why? Because if you see the equation now, which was error plus lambda into B square, right? When it is ridge, right? It's like squared. So in that case, you say that this penalty is 0, which means that this portion is 0. So still that error is same error. No point. Okay. I hope everybody got it. So once again, removing that, stopping annotation, and slideshow. The rest all things same. Like we say, model is model dot. Model dot fit to train the model. Model dot predict to be done on testing data for X values. So Y predict you get it, right? And then what we do is we print what is the outcome of polynomial regression without regularization. We get the R square train values, right? Test values of R square, train values of root mean squared errors, and test values of root mean squared error. For everything, I have given you the equations and all, right? I hope everybody remembers that. Isn't it? So here equation is, okay. Do I have colors? Shape it is. Thick it is. Pen vanishing, pen, highlighter. Okay, no worries. So let me give you the equations once again. So when I say R square, it is 1 minus your summation of Y predict minus Y actual the whole square divided by summation of your Y actual minus Y average the whole square. When I say the root mean squared error, it is nothing else but Y predict minus Y actual the whole square summation of that under root of that divided by total number of observations. Right? And what is my equation? Like what is my model? So model is equals to, let's say, make underscore pipeline. Then I do a model dot fit. Then I do model dot predict. How can I get the constant and the coefficient value? Anybody? What I have to write to get the constant value or the coefficient value? Model dot
COEF underscore E.
yeah, model dot coef underscore will give me coefficient values of all the variables, and I can create a data frame, right? Constant model dot intercept underscore, right? This will be intercept or the constant. Again, let's do that. Then after that, I'll be showing you. We'll be creating, again the, sorry.
Small question, Ravi.
Yeah.
Why we have ridge 0 on the last slide?
No, it's only iteration. See,
Okay.
I'll tell you what we are doing is we are simply experimenting.
Okay.
You can put anything like nobody stops us. Like you can put ridge as 1, 2, 3, 0.001, whatever. There is no limit to that. In coming days, I'll give you one technique by which you can try multiple values. We call it grid search and random search. Okay, remember, grid search and random search will be the idealistic way of fine tuning any multiple aspects of a model, because you can give a range of your numbers. It's not only zero, it could be 0 to n. You can do that. Okay, so that is grid search. Random search is that we'll be assigning some random values. Okay, I mean, random search would be like just assigning any random observations. So I'll teach that. But yeah, in the ridge regression, what we're doing is alpha is now set to 1000. Your answer is now there, right? Now they're experimenting with 1000 and same thing. Then they are also saying let's have 10,000 iterations. Like it will take too much time, right? 10,000 iterations. Keep alpha equals to 10. Alpha is what? The penalty, right? Of what? Lasso. Now they say lasso, let's try that also. Then get the actual versus predicted plots, right? For what? For test sets. Which model? Let's see which model is this. It's like lasso, right? Lasso test set. They are getting actually on that. So I may have to use this y underscore test for lasso for getting this. Then lastly, we'll be discussing why model evaluation matters in regression. What is mean squared error, root mean squared error, mean absolute error, and R square, right? Then I already discussed what is R square. I'll again further give you the evaluation aspects. We'll discuss R square, training R square versus testing R square versus gap of the R square values. We'll see actual versus predicted plots, key takeaways, and then this is winded up in 15 max minutes. So very quickly, coming back to the notebook, you may find the notebooks in your drives. So let me show you. Hey guys, please confirm. Is it interesting? Are you really enjoying the session? Please confirm. Are you with me for the discussions?
Yes.
Yeah, yeah.
Yes.
Yes, Ravi.
Yeah, because I'm trying to make your life simple, so that's why I'm giving you all the hacks to remember the codes, to remember the functions, formulae, whatnot, right? Only that we can do right now. Trying to provide some analogies, right, wherever required. So first of all, let's have the important libraries. Only this part is new, Ridge and Lasso. You can see my cursor on Ridge and Lasso. From where we are getting? From scikit-learn linear model only. Okay, because it's a regression model, right? From there only you get the Ridge and Lasso. When we deal with neural network, then also I'll show you the things. Let me run this. To load the dataset, I need dataset housing data, right? So I need to upload it on my collab. It may take a minute. Or I think now 50 seconds. Let me hide this floating control. Where it is. This is housing data. Getting it uploaded, guys.
Just a quick question, Ravi. Hello.
Yeah.
In the last session, we saw the majority and minority of the data which needs to be fitted, right? So in
No, that is
this,
oversampling, undersampling. That's
yeah. So now here we are seeing lasso and regression, basically also to normalize the data. So what is it? I mean,
No. It's not to normalize data. Actually, it is to bring down the accuracies.
okay,
Simple. It's nothing doing with sampling. Actually, that
okay,
is a different bias. That is actually the target variable was a classification model. I mean, the
okay,
model of classification target variable was having multiple groups. One group
okay,
was majority, one group was in minority. So that's a biasness removal. That's it.
okay. That use case is different,
Actually,
and okay,
yeah, that biasness is not by P minus by actual biasness. It is actually biasness with respect to gender, caste, creed, target variable, anything.
okay,
Okay.
okay, okay,
Favoritism. Yeah. That bias is favoritism, more psychological aspect. And also that is helping, I mean, that is corrupting your model, right? You don't have fraud people. How can you train a model for predicting fraud, right? That's it. That's a different story. So let's see the data is there or not. So I just run that. The criminal rates, sorry, the crime rate to house price, we have all the variables. Okay, that's it. So we did X and Y, making the life simple. X is what? Every variable apart from house price. So that is getting dropped, the house price. So that rest of the data frame is having DF, right? The DF is equals to all the data except house price. Y is what? Only the house price. So we are, extracting house price only from DF. I hope since many times you're doing it, so you're aware. Then we do a train test split, nothing new. Then we create a polynomial degree mechanism, right? We set the degree as 2, 3, 4, whatever level of polynomial aspects you need to work out. You can go ahead. You are using a pipeline methodology, which I discussed last time for data processing. Here it is for model building. Make pipeline is good here in case because we want to attach multiple things. Polynomial features to be created with degree along with a ridge regression. Here it is 0. Alpha is set to 0. Then we are saying polynomial model dot fit instead of model dot fit, whatever name you want to give, you can put any name, right? Einstein is equals to make pipeline, right? Einstein dot fit is model training. This is important. Train and X train and Y train. The model is actually trained on that only. So I hope everybody remembers that. Model is, these are like quick hacks and you should remember that. What is that? Where is my pen now? Oh, just a thing, guys. Okay, here it is. So please remember, whenever we are saying model dot fit, okay, this data is always on X train and Y train. Don't get confused. Don't put X train and X test. And this for training data. If you are using a testing data, you can put that X test, Y test, which is ideally not done many times, right? Rare people might have done that because we want training data to be large. Because test size is always 20%, right? Biased things are there already. Apart from that, when we say we are going to dot predict, model dot predict, this is always worked out either on uh, your Y test data, right? Majorly it is to be done on new data set, so it is Y test data. You can also get that on a train data, by the way. Nobody stops you. So you can also have model dot predict on Y train as well. So training values predictions and testing values predictions. Next thing is that whenever you apply any metric like RMSE or whatever, so RMSE is always brought down. So model have that RMSE score. So let's say RMSE square score or R2 underscore score is always implemented on Y predict and Y actual. Okay, guys, this should be always on Y predict. which is y predict for you. Y predict is this. Y predict is always this model dot fit x train and y train. Things to remember. Still any doubt? Let me know. So what we did? We did that workaround, basic workaround. We splitted data. We made a pipeline, and we get the output of all the aspects. Number one, polynomial with degree 2, make a pipeline with polynomial degree, which is 2, rich, implemented here in comma, separated, and write alpha equals to 0. Alpha is your weight penalty set to 0. What if I, okay, first of all, remember that my R square is 91% for training data. For testing data, it is 80%. Can you see it is basically overfitting? Your higher accuracies are for training data, and for testing accuracies are, you're seeing it's bit reverse, right? In this case, training accuracies are good because you can see root mean squared error. Error is less in training data. Error is more in testing data, which clearly indicate there is a overfitting. So let me try to tune this alpha as, let's say, 20. Okay. Still there is no difference, right? Let me take this to something as 20,000. Now it's somewhat similar. Can you see that? Attaching a penalty like this is making it almost similar, 85, 83, 3.57, 3.43. Hope you got it. So how do we treat it? How we manipulate that penalties with the errors, right? To bring down the accuracies. 91 is brought to 85, and the poor testing data accuracies, which were 83s. The idea is what training and testing accuracy should be consistent. Even if it is 85 and 80, 83 and 83, that is also good. Once you say 98% on training and 80% on testing, nobody will accept your model. If it is 85 versus 85, this is consistency. Please confirm, guys. There is no biasness. Because though the testing data is less, still your model is able to predict that. Actually, that is the gap. I mean, that is the catch. Okay, let's see at 10,000 what happens. Where is my pen? So let's see if I do it at 10,000. Still that is working, right? 86, 84, and slightly higher accuracies are there for testing data now instead of 83, isn't it? So this is a hit and trial. So can I do that instead of, say, rids, if I put something as lasso, and when I do a lasso, I can still work out that. So in lasso, it's 36, almost same, but it is nobody accepting, right? Hey guys, am I audible? Please confirm.
Yeah. Yeah.
Yes, Ravi.
Though it is like almost very close, but this is also not doable because in lasso, the errors are dropped like accuracy is dropped like anything, right? So we have more errors there. 6 and 7 units are there. What is the interpretation of 6 and 7? Anybody? When you say you have 6 and 7, what is the interpretation here? R square, as I mentioned, it is nothing else, 1 minus bias by variance, which is somewhat you can treat it as accuracy, but this is not ideally accuracy, it is percentage of explanation, which means that your model can represent 36% of the variance by the variables in the data. Okay. Remaining, let's say, percentage, okay, 64 something, right? So in that case, this percentage is not exhibited properly. Means you need more variables actually, or more complexities. So therefore, we have to go for grids.
Dr. Ravi, can you explain one more time the last part?
Okay. So R square, don't say that it is accuracy. Okay. Though it looks like that, it is 1 minus error. Don't call it accuracy. It actually is what? It is percentage of variance explanation of your model. What is that percentage of variance explanation? It means that whatever the variables are there in my data, they're actually making my explanation they're explaining 36% of the variation happening in my data or model. They're not able to capture, let's say, 64, 65% of variation, which means that variables are not sufficient. Seems like that. Okay, but actually the ideal case is what we have attached less, so that's why it's happening. When I say root mean, this is the error. This is the actual error, right? So here won't get the accuracy of 70%, 80%, 90%. No, it's not like that in regression. In classification, you can get that. Here it is purely, as I mentioned, the metrics which are there for evaluation, they take the units of actual data. Here the data is units in dollars, house price is in dollars. So there's $7 versus $6. Now interpret please, anybody. So whenever you are saying that this model is implemented, and whenever you are predicting house prices, let's say I predicted for X observation, house price to be $10,000. Root mean squared error is 7.45, for example, which means that it will be either plus or minus $7.45. That's it. Upper side also and lower side also. We are not defining it whether it can go lower side also, upper side also. So it is $10,000 plus $7, which ideally is not that bad. Like it's $6 to $7 kind of fluctuations.
But the model accuracy, generally we take the percentage of the error.
No, nothing like that. It's only in classification actually.
Okay.
That is known as accuracy score. Here it is nothing like that. It's a regression model. So it's always a unit, which is actually the data unit. So it's plus and minus this much dollars error would be there in predictions. Yeah.
So it all depends on the price also, right? $7 or $6. Sometimes it may be more also at the point, correct?
Yeah. No. So this root mean squared error is basically on an average, you can say that for current data sets. In real time, it can grow also. That's why you have to keep a watch on every month, every day's price and error. So that's what I said. You have to keep a watch on error plot. This is known as error plot. Like we create for Y predict, you also need to trace errors. If error is like this, we wish that errors are always constant, come whatever time is there. Every month error is same. We need this. Error is there, but it is fixed. But what if your data is having these kind of things, right? This is time passing by and this is the error. High, low, seasonality is there in errors. This is known as heteroscedastic event. Error is not normally distributed. Okay, guys? Enjoying? Next is, yeah, I think we did that, right? We changed to lasso also and all these things, right? You can try multiple.
Here what is small doubt, Ravi, Dr. Ravi.
Yeah.
So here, what is the purpose of the variance of 36%? Like, is it kind of like a standard deviation kind of thing?
It is
36.
nothing else. Yeah, I'll tell you it is just the percentage of variance escalation means model is fit or not. This value should be higher than 60% to see that model is completely understood, at least somehow understood. 60% variability is explained by variables. Please understand. Hear the line very carefully. 60% or let's say 36% of the variance is explained by variables, which means that 64% of the explanation of the variation in the data is not explained by variables, which means that my variables are not variables, they are constants.
Okay.
Please understand.
Is it nothing but the spread of the bell curve?
Exactly.
Okay.
I mean, to some extent you can say, but not 100% that, because it has nothing to do with that actually. It's purely on bias and variance trade-offs.
Okay.
And with respect to that one minus that equation, right? So that's what I'm saying. Please take classification separate and regression separate. R square model fitness. R square is nothing else but a model fitness test. If more than 60%, I'm happy. There is no benchmark.
Dr. Ravi, so can we understand that if the R square is good, the model is able to explain all the variables, all the data properly?
No. All the variables are explaining model reverse.
All the variables are explained.
Yeah. All the variables are able to explain the model in a decent way. I mean, they are actually variables, they are not constants. If r square is 0, you mean that there is no variable. These are all constants because there is no change, right? Like that.
So if R square is,
100.
good, like greater than 80, so that means the chances are that the errors will be less. Is there some connection?
See, I'll show you one experiment, right? Where you'll get r square is almost closer to 99%, 99.9.
Doctor, just for understanding, can you also run again that ridge one more time just to see how is the RMS error is coming? I didn't notice in the last time, so it will
I'm
come
sorry, I
lesser
didn't get
than
it.
this.
Can you come again or somebody can elaborate what you're asking for?
Can you run the ridge one more time? The
Oh,
RMS
sure,
will
sure.
be it will be further lesser than the 7.45. I just
For
want
sure.
to
I think it's more than 80%. Yeah. So I'll also tell one more thing. If R square is like 100% of this happens in time series data actually with the stock price kind of data sets, which is known as spurious regression. If R square is dangerously high, it leads to one term that is spurious regression. You can read on internet. Spurious regression is false regression. Means it is a highly idealistic model, like noble gas equations. So nothing is that ideal, right? Like that. So let me run the ridge again. So let me change here itself, right? Okay. So what I'm doing is I'm saying that it's ridge. And what alpha you want or to be tested on ridge?
same 10,000.
10,000 works. Let's see. So here see with the ridge, this model is better. And let's see the error also. It's like less, 3 units only.
It is 50% almost.
Yeah. With 10,000 it is good, but with let's say something like 10, I don't think so. There is a gap, 90% versus 80. It's a overfitting. Reverse is underfitting. This is training is more accuracy. You can see training is more accurate and testing is less accurate. With that, we see the last item of this topic and we take a break and we come back and we do the next model. So like that, they did the lasso and all, right? Maximum iteration, you can say, you can also put maximum iterations. Let's see how much time it takes, right? Let me do one more thing.
I don't remember the equation for root mean square error, but it looks like the R square is proportional to the error also, right? So in your previous explanation, right, you were mentioning some kind of regression, right, where R square is 99.99. In that case, error is also very low.
Error is low because that is a spurious regression, which means that actually I'm taking the data as it is, and the data is almost similar to each other. The data point.
Memorized, okay.
They are highly correlated actually. Yeah.
Okay.
Because let's say if I predict close price and I have another variable like high price, low price of the same day, it is almost the same record
Yeah. Yeah.
of the same stock, right? That's why the RS square will be high there.
Okay.
So when I say percentage time, right, what it does is it helps me to see how much seconds were used for this calculations. So for 10,000 iterations, microseconds were used, right? Let's say if I do this, increase this iteration means you can see one model, second model, third model, fourth model, like that. There would be a number of calculations which might have done. Now it's slightly 4.77. It's all like optimized, right? Still. Anyways, but yeah, 8.34 microseconds. You can see. So then we plot what? We plot, sorry, I think I explained that, right? It is nothing else but lasso based model, which already we did. Then in the end, we take the lasso based models, y actual, y predict, and build a plot. So scatter plot is there. We set the alpha, this transparency. So if I set this to 20%, you will see that the transparency is like gone, right? So what we do is we see this plot with actual prices versus predicted prices. Standard line is passing through between, and the blue dots are nothing else but actual values. That's it. Okay. This code is available with you guys. You can practice that once again. You can do that.
Dr. Ravi, one small question.
Yes, please.
In our case, basically all we are doing to improve the accuracy of the data in our scenario.
Model, yeah.
So in the previous classes, we saw to normalize the data. So in which use cases we normalize or we
No, for this use case also you should do that. Actually, we have less time, right? So you are
Okay.
skipping those steps. But yeah, that is a standard process I mentioned. Not every time I'll do that, but remember that is should be ideally done. Okay, for every use
Okay.
case, even for this data also. Because if you see the data, let me show you. I think it's upside. See, this is in tens, right? This is single unit. This is in decimals. So that standardization is required here also.
Yeah.
Then you get better results. But we have less time to discuss again and again. Otherwise, it will be like 2 hour session again on the same thing.
Okay.
So don't forget that part. Data processing library, sorry, notebook I have shared. Try to practice that for every use case almost and bring that accordingly. So let's take a break, guys, for 15, 20 minutes. Sorry, not 20 minutes, 15 minutes. Let's come back and let's start the next chapter of our module that is going to be probability based module. So Bayesian side of operations. That's it. Somehow it's like, but the mentioned is KNN, but I think it's evaluation with respect to log loss functions. Okay, let me check which model here we are working upon. So here we are working upon on the strange, guys. I mean, one thing I would like to mention here, like I could see it's KNN mentioned there, but that KNN is like reverse. Like we are discussing that KNN in the end, and then doing the evaluation first. So somehow title mismatch. Basically, this get confusion. No worries. Let me do reverse, guys. Let me tell you the decision boundaries first, the algorithm first, and then the evaluation. Would that be okay for everybody? Please confirm. Okay.
Okay.
Sure. So again, I have to go back to my whiteboard, right? And to do that, in terms of evaluation, the major thing which actually decides everything is confusion matrix. And I hope we have gone through the confusion matrix calculator, where you have seen all the formula regarding F1 score, true positive rate, false positive rate. Please confirm, everybody. Right? I think multiple times I have discussed the classification evaluations, right? What are the true positives? So let's say the case of 0 and 1 is there. And when exactly the case is going to be true negative, true positive. If this is predicted, this is actual, then predicted is 1 and actually 0. So it's like false positive. It's a false negative, like that. And basis these particular aspects only, the evaluation is being done. So it's all being discussed. But once again, we'll see. We have so far using model.predict function. We'll be using now model.probab, P-R-O-B-A, probability, model.log loss. Okay, these two new functions we'll be seeing in this agenda. Let me discuss one by one all the three things. To begin with, K nearest neighbor. Okay, there are multiple formulae to work out on a KNN format. Logic is very simple. In KNN, we try to have a decision boundary. What is decision boundary? Suppose there are three instances. Person, will buy a stock. Person, let's say, will buy a product. Person will not buy new stock. Person who exactly is neutral means he's holding whatever he's having right now, not going for a further buyout. And when he says buying, it's a new customer who is buying new product. So there could be a number of use cases like that. So let's say there are three different types of observations. Okay. So let's say this is variable one, and this target variable. Target variable is classified as, let's say we want to classify these objects, whether the particular person is having a cancer or not having a cancer. So 0 is like all the patients not having cancer. Let's say benign. And 1 is malignant, means persons are infected with the disease. Malignant kind of situation, having a cancer. This V1 is nothing else but, let's say, cell size. So how do we classify these observations with respect to k nearest neighbor technique? Okay, k nearest neighbors. That's the division boundary here. So like that, you will see some of the observations are lying here for multiple patients. For some patients, observations are lying here. For some patients, observations are lying there. Okay, some would be in between. So randomly what happens is we try to pick any observation. The model try to pick any observation. Let's say this is one observation which is randomly selected. This is another observation which is randomly selected. This is another observation which is randomly selected. What happens is we try to calculate then the distance with respect to all these objects. So this observation and then its nearby object, this object, like that. So how the distance are calculated? Last session I mentioned that this is one observation, this second observation, this third observation. Let's say this is my central observation. So I have one observation here, I have one observation there. I can now create a triangle, and that becomes my hypotenuse. So this, let's say this is O2, A and B. So AB square is my hypotenuse, which is equals to nothing else but it's under root, AB is nothing else but under root of your AB square plus OA square. From early childhood days, we know that, right? So there's the best in class analogy of KNN.
OB
There are
square, right? It is OB
Sorry?
square plus OB square plus OA square.
So OA square, yeah, sorry, and OB square, my bad. Already this particular AB is to be calculated. So this side square and that side square. Thanks for that. Okay. So from childhood days, we know that Pythagoras equation works out. Same to that, we have distance calculation. We have Euclidean distance, which is similar to this. There is something known as Manhattan distance, right? Chebyshev and whatnot. So multiple formulae are there to calculate it. Okay. Now, basically, the most common is Euclidean distance. Okay. Be it clustering mechanism, be it your classification with respect to k nearest neighbors, we try to see that the distance is calculated. Now, what I'm saying is it is nearest neighbors. So where are these neighbors? What are these neighbors? So let's say I select 3 neighbors. So this distance will be calculated for these 3 neighbors, and then objects will be classified like that. So first set of observation will be distance between 3, then distance between these 3, then distance between these 3, then distance between these 3. Like that, you will see. This will be for every observation, this will go, and slightly you can demarcate observations in multiple classes, right? Basis their particular occurrences. So somehow you can see that though the cell size is there, still very high, they are on a borderline cancer for these patients, right? Their cell sizes are low and therefore they resemble more to zero cases where no cancer is there. These are patients which are having somewhat moderate, let's say, cell size and they have cancer. Ideally, what will happen is for these patients, the cell size would be high and abnormal, and the cancer situation would be like that. Just hypothetically, I've put this data, right? So it depends how exactly they're going to work out. Then there is one more aspect to it. What is that aspect? Uh, what are the different types of formulae and all this, distance mechanisms before getting into the algorithm part, and where we are going to get this model again from k nearest neighbor. Again, we can leverage it from scikit-learn model, k nearest neighbors classifiers. It's a classification algorithm. So it can be also used for regression as well, by the way. Okay. Any doubt till here? Now let me tell you the exact equations for multiple types of uh, equations. So resemblance I have given, the distance calculation, that's more to do in Pythagoras way. But ideally, if you talk about different methods, like say Euclidean. In Euclidean, the distance between two objects is measured as distance between x and y observation. It could be, it's not target or something, it's basically any two observations, right? As under root of your summation of the value of your x item observation 1 to n, and till then it's like observation y 1 to n, and the square of that. It's like a deviation, it's like a variance part most of them. There is Manhattan method. In Manhattan, distance is calculated in almost similar way. The only thing is, instead of squaring it, in this case, what ideally we do is we are taking summation, removing the root, and taking the mode values, like absolute values of xi minus the difference between yi. Objective is simple. Here, with a square value, we are actually avoiding the minus sign, and here we are taking the absolute values to avoid the minus sign. So to get the distance calculation, there is no recommendation. Like in this case, you have to use Euclidean. In this case, Manhattan. People have come up with their own formula in mathematics, so that's it. There is nothing choice of which distance calculation has be more effective, situation based. So for large set of observations where the scaled values are not there, you can implement this, and you can implement with this with less complexity of data. That's it. There is last equation which is Minkowski, right? Let's say Minkowski. Minkowski has said that we can have the distance calculation like summation of absolute value of xi minus the difference between yi to the power of p, and again the entire equation to the power of 1 by p, and nothing to do with this p. This is nothing else but this is like number of neighbors and all. So not neighbors ideally, it's like Euclidean values, right? So for example, p is equals to 1. Okay, in that case it is similar to a Manhattan kind of model. If p is equals to 2, it's more of a Euclidean format, isn't it? So if p is 1, it's same like Manhattan. But if we say it's 2, power is 2, it resembles Euclidean. I don't know why. they have done that. But anyways, what is the final goal here? To minimize the distance so that we can classify under the same group. So the objects which are having least distances can be clubbed under class 1. Objects with more distances can be kept under class 2, right? Even this distance can be calculated. So that's how exactly we calculate the distance mechanisms. And we want that the inter-group distance should be more and intra-group distance should be less. That's the objective here. That's the mathematical workaround on k nearest neighbors. Again, I repeat, k nearest neighbor is nothing else selecting the observations, calculating the distance dependent on neighbor. Take 3 neighbors first, 5 neighbors first. It all you can define in the model. That's it. Check the impact on your algorithm, the accuracy. That's the final thing.
So,
yeah.
One question I have. So in this model, the Minkowski's model, if P is cube, then it can have a negative value, or it's absolute. This one is also should be an absolute value.
See, what you're saying is, like, say you have xi minus yi, right? Let's say this xi is what? 4. Okay. Y is what? 2. Now see this. So 4 minus 2 is what? 2. Isn't it? We are taking the absolute value, by the way, and then taking the cube of it. So
but even on this one too. Okay, got it. So yeah, even if it's x is 2 and y is 4, still you'll get the cube of it is also
so,
like.
correct. So let's say 2 minus 4, you do reverse it.
Then also it's absolute.
Correct. I mean, it's only there I think mathematical discussions and I should say their own orientations. Nothing I see a big difference happening there, in terms of distances. Obviously, whatever method you have tend to calculate a distance, and basis that distance, you are keeping the objects near to each other, and basis that you can select the decision boundaries, right? That's it.
Okay.
So one more game is attached here. This game is probability, right? So when I say with what probability, okay, what should be the probability? So I can say that if probability is more than 0.50, can it be classified as class 1? And let's say, can I say that less than or equals to 0.50, it's like class 0, like that. So this is again the decision boundary we have. Additional complex situation is that what should be my probabilistic value? For that, you will find that in evaluation, we do something known as, where is it? ROC curve, right? ROC, area under curve, and then we have receptor and kind of, the curve which is there, ROC AC curve. So area under curve mechanisms are actually utilized to see this thing. What is that? Let's say we have 0 class here and 1 class here. Okay. So if this is one particular observation, I mean, number of observations are there. We have this area under curve is like this. When area under curve is almost giving you the value of 100%, it means that if this value is 1, AUC value is going to be 1, right? It means that when you are actually distributing all the observations, right, there is no overlap between 0 and 1 cases. So all these cases are actually what? Under the curve are true negative cases. All these cases are true positive cases. Whereas if it's 50%, you can have such kind of overlaps where this portion left side is going to be what? This is 0, this is 1. So 1 becoming falsely as negative, right? This is actually 0, but we are predicting it as 1. So this is false positive. And reverse is happening here. This is actually 1, but we have predicted that as 0. So false negatives. So let's say 50%. So this is area under curve kind of measurements. We'll see that also. Okay, that if it is 100% means there is no overlap between 0 and 1 cases, true positive, true negative cases. If it is less than that, somewhat 80%, it is also okay. But 50% means acute overlap. Like some of the cases will be like this: false positive and false negative. The area will increase. And just imagine situation like this. You know? So this is all we have to understand. I think I've given more technicals and all these discussions formula wise. Let's come back and see something on a slide and then come back to the uh, algorithm part. So let me just avoid this floating meeting control. Before that, I need to stop annotation, come back to next slide. All right, guys, slideshow. This is all actually the accuracy scores, right? I'll come back to this. Before that, let me see if I can have something on our decision boundaries. So how exactly the classifiers are splitting the classes? I have given you the decision boundary on distance calculation basis, or it could, last time we discussed support vector machine, which is linear regression kind of equation, but for classification. So purpose is that how do we split the class? How the model can separate the classes, right? What are the key characteristics of this particular, objects? How do we understand these models? Like how do we generalize these models, and how these models are going to reveal the relationships between the target variable and independent variables, and what are the changes within the model type and feature transformation? How do we do that? So let's see what a classifier changes, where a classifier is going to change its prediction. For example, definition is that point where the model's class prediction shifts, as I said, that 0 converting to 1, 1 converting to 0, their differences are there. And ideally situations are there where exactly we have decision boundary exactly as 0 versus 1 are separate altogether. In two-dimensional objects, let's say data sets and all, it's like linear models can be worked out. But when the data is curvilinear or non-linear, in that case, we may have to work on multiple separables. I have shown you, if you remember the video of support vector machine, where the observations were intermingled like anything, and we couldn't separate them. So we inserted one hyperplane, divided that into a curve, and then extracted that piece of observation separately. Otherwise, I'll again rerun that video, right? So logistic regression basically is the regression-based classifier. K nearest neighbors is like most oftenly used for irregular observations, right? Like as I mentioned, intermingled like anything, and it's very difficult to separate them in two separate classes easily. So logistic regression looks like this. You can see the chart, like how exactly the picture looks like. Very clear classification and decision boundary between two different types of classes. One observation is blue, which is error part out of multiple things. But non-linear decision making models are kernel, support vector machine, decision trees, k nearest neighbors, and whatnot. So we have non-linear models as well, which is support vector machine. What it does, So for example, sorry, again I have to go to okay. So here you can see that when it comes to support vector machine, I mentioned that in a linear model of support vector machine without any kernel approach, decision boundaries are very simple. You have observations like this. You can insert a hyperplane like this. And insert means like you can create a regression equation, y is equals to a plus b of x kind of thing. And from there you can calculate, you can create one more marginal line here, hyperplane here. So let's say there's one particular plane number one, plane number two, this average or the standard equation based plane. So this support vector 1, this is support vector 2, supporting the marginal observation. The thing is that the distance between this observation and this line and this observation, this line should be equidistant from the center. That's how exactly it is being designed. It is very easy then in linear fashion. But if you want to have some observations which are intermingled and we can't separate them out easily, right? Say these observations are from that another class, which is the right side. This observation are from this side. So actually in that case, there is a hyperplane which is a quadrant structure which goes inserted, and within that we create some kernels, right, like circular or non-linear, and then separate them up with these observations outside this. I'll show you with the animation. So in that case, use the support vector non-linear kind of models. Very difficult. This RBF is to be used in that case. This is known as radial basis function. Don't get into equation for that. It will take another 30-40 minutes to calculate radial basis function. But when we use non-linear model, we say that support vector classifier attach kernel equals to RBF if it's non-linear, attach kernel equals to linear if it's linear. That's it. So you can change the kernels. Okay. Then next part is there are particular libraries, ML extend, which is used majorly for recommendation system for market basket analysis and all. Matplotlib, NumPy, which you can work out, and ML extend is basically used for plotting the decision regions. So you can see that this kind of graphs can be created where you can clearly demarcate them easily. I'll show you with a notebook, right, how we can create these lines and triangles, squares, whatnot with Matplotlib ML extend. So we have simple models where linear boundaries are there, very easy models, right? But complex models are those where we have tight contours and we have risk of overfitting issues, and it's very difficult to work out on them. So logistic regression versus high degree polynomial support vector machine or radial basis function based support vector machine is to be worked out here, right? So when the model actually learns too much, overfitting happens. Large data, large observations, number of observations, model complexity increases. Model learns a lot, get the best in class accuracies. The thing is that we have to then work out in adding noise to the data, decrease the error part, decrease the accuracy part, right? The classifier, if you see, logistic regression is most oftenly used. What is this? Logistic regression is used when the decision boundary is linear. K nearest neighbors equals to 1 means something is irregular. In that case, you can use it. When you say number of neighbors, okay, if you say that you are going to have 15, okay, so in that case, things would be further easy for you. So this is all iterative. I mean, you have to hit and try. I'm not saying this is like 100% going to be exactly same, right? This is again hit and try. SVM support vector machine based radial basis function kernel is utilized when the linear relationships are not maintained. The curvy linear relations are there. It's like 3D aspect which is coming in. I can't even design that, curve there. So decision trees basically used for the decision boundary where we have dichotomy in decision making. For example, I'll go out today. Depends on whether I have some reason to go out, yes or no. I don't have a reason. Then why I'm going out, right? So is it like I want to simply explore the world or just to meet some friends? There is no reason. I'm just only exploring. But other aspects which I now need to understand is that do I have a conveyance? What is the timeline? What is the humidity aspect? What is the weather condition? Right? Multiple things come to the plan. So it's a hierarchical tree-like structure when it comes to decision trees. We'll deal with them decision trees, in separate class. It will again be like entire session on decision trees. So there are transformation mechanisms which are required when we talk about the methods which are polynomial features or kernel tricks. There are multiple ways by which we can create more expressive boundaries, right? We'll have to showcase that. How do we do that? So transformation, as I mentioned, features can be added. Complexity can be added actually. So if data is underfitted, we can go for a polynomial thing because that adds more complexity to the model. Model becomes complex, variance increases, and underfitting becomes overfitting kind of thing, or let's say optimal fitting. So we'll discuss that now, linear logistic regression versus curvilinear, how it looks like, right? So there's a curve pattern which we see in demarcating multiple classes. Okay. So it's a linear pattern, there's the curvilinear pattern. So how do we visualize decision boundaries of classifiers? So we'll be demonstrating that, how the classifiers split the data and all that, right? And I'll be demonstrating the k-nearest neighbor implementation and model evaluation all together, right? With a notebook. Now come back to evaluation patterns. I have multiple times repeated that, so I'll not be repeating this. The calculator approach, but I hope you still remember those things. The best part to understand the evaluation pattern of a classifier is this wiki content. Okay, sharing that with you guys. Let me hide floating meeting control. Let me come back here. Classification evaluation. There is no better way than what is being mentioned here, to be honest. There are so many confusions I had, while dealing with confusion matrix. Its name is also confusing, right? So to make it easy, what I did is actually I went to confusion matrix where I have seen that how exactly the values are kept as true, positive, true, negatives. And in those scenarios, ideally you see almost all the matrices, right? True positive rates. Then we have BM workaround, bookmaker, let's say the calculation of the metrics, prevalence thresholds, false negative rates, how they are being calculated. So n number of things you will get from these matrices, more than what exactly we have right now. Okay. So I wish that if you can go to the entire workaround here, which basically helps you to get almost all the doubts clear with respect to multiple things. Apart from that, there is one more thing which exactly comes on the way. So confusion matrix from scikit-learn, right? So it gives you every aspect, right? All the formula and all these things can be learned from here. I mean, multiple things are there for confusion matrix. It's never-ending kind of a thing, right? Can you see that? How many types of formula are actually there when it comes to confusion matrix or classifier evaluations, right? So obviously we can't deal with all these matrices. You have to hit and try and then see which are the best, but the most common things we are going to discuss now. So the most common things which exactly come on the way is a basic confusion matrix. So actual positive, if predicted also positive, it is true positive. Actually something is positive, I predicted it negative, false negative. Actual is negative, predicted is false. Sorry, it's positive, it's false, positive. True negative is that where actual and negative and predicted also negative values. But basis these four items, multiple formulae have been created. The only thing, best thing which you can do is to work out like that. I remember I have discussed that when the numerator is mentioned as true positive or true negative, its value should be closer to 1. When something in the numerator is kept as false, be it negative or positive, it should be closer to 0. That's the only quick hack you can understand. Difficult to remember all this multiple formula altogether. right? Let's say accuracy score. True positive plus true negative divided by true positive plus true negative plus false positive plus false negative, all the items taken together. This is the accuracy score, right? From where you get it? Scikit-learn has metrics function. Metrics has accuracy underscore score function. You can implement is always on y test and y predict, as I mentioned last time, a few hours back. And what is the quick hack? Wherever numerator is having something true or maximum true, then it is going to be always closer to 1. It's a true instance, right? The value will be true for 2 would be higher. That means that 100% accuracies should be achieved with one value. What is ideally recall is there, which is true positive divided by true positive plus false negative. What should be ideally? Please tell me. Shall I expect 0 or shall I expect 1 for this recall? Anyone?
One.
1.
1, right? Because it has true as a numerator part. Very simple to understand. Then it is like twice of precision and recall divided by precision plus recall. This also is basically closer to 1 is ideally expected F1 score. It is actually combining two things, precision and recall, into one score. What is precision recall? You can see that it is recall, true positive is there. And when it comes to precision, it is also having true positive there. But in downside, there is no false negative thing in precision. In recall, there is false negative thing in the denominator part. Okay. So when to choose precision, when to choose recall? I need one particular example from anybody. In which case, we shall be concerned about recall when we shall be concerned about precision. You have the answers in front of you. Here you can see it's all about false positives, positives, positives. Here you can see that it is positive, but negativity is also to be understood.
It depends upon how you like what place the false positive and false negative will play a role.
Okay, let me put another question. We are almost there, but let me make it simple. Suppose that you have to build an application, and this is a customer churn prediction. Customer will churn, will not churn. So tell me whether you're concerned about precision or recall majorly. Majorly, I mean agnostically, so you can say that I need both perfect. Okay. But agnostically, if I talk about that, but biased way, like what should be more concern for you? Predicting wrong a person, he is living and he's not living actually, versus predicting that he's not living and then he happens to leave, which is major risk as a business.
He's leaving but not predicting is leaving.
You predicted that he will leave, right? And he's not living, is that?
No.
Uh-huh.
It's like he's leaving, but we are predicted as not leaving.
Yeah, you said that he's not going to leave. Okay, he left. Is it false positive or false negative? You predicted that he will not leave. It's false negative, right? Isn't it?
Correct, yes.
So recall is a concern here, right? Like that, you have to understand. I mean, you have to just try by yourselves, right? Go through the deck again, see multiple times, multiple types of instances, which is scenario where exactly you're concerned about it. If you talk about this with precision, uh, what could be the ideal case here is like uh, you predicted that the person is actually should be given punishment, right? And he's found to be what?
Not guilty.
Innocent.
Not guilty.
Mhm. So likewise, there are multiple scenarios which happen in business. Sometimes you have to sit back and then understand which is my concern. Is it like I'm predicting something else, false positive or false negative is my concern, right? False negative is your concern means that something which will happen if I predict something is not going to work out, but it goes out, right? The customer goes out. And in reverse case, it will be false positives. Likewise, like it's a bit tricky, but yeah, multiple times if you observe these kind of scenarios, you'll get to know. Likewise, there is a specificity. Specificity is again true negative divided by true negative plus false positive. Though we are considered about negative cases, but it is true cases, right? Still, we should have that maximum values. That's it. So here my concern is true negative cases. Here my concern is true positive cases in both this. Okay. All right, guys. So let's see. All this I think we have done multiple times. Like one more thing is that the trade-off between true positive and false positives, right? I mean, in that case, I mentioned that the curves can be utilized, and how it basically is worked out as false positive divided by false positive plus true negatives. All right. This is the ROC curve, as I mentioned. Area under curve in this case, if it is closer to 1, means that there is no such overlap. Right. So let's continue this. I think the next week, I wish to showcase one notebook also. So I'll again discuss this from here, and then we'll pick up the next module as well. Right. I think that would be ideal scenario. Okay, guys. So let's connect in the next meeting. Till then, happy weekends, and let's connect by next week.
Thanks, Ravi. Happy weekend.
Thanks. Thank you.
Thank you.
A nice weekend. Bye.